So let's start with a review of today's class. Today's a simple class. It's really the equivalent of, let's say, the Gaussian distribution, but now for discrete data. So this multinomial distribution, the categorical and the Bernoulli, they're associated with basically the essential or the typical experiment for discrete data, which is throwing a coin or throwing a die and then watching on which face it lands, right? And then making predictions. And so then we do that. We set up in this class a likelihood function and a prior, and we basically execute Bayes' rule. And when we do that with a Bernoulli distribution and a beta distribution, or for the multi-phase case, so more than two phases, the category distribution together with the Dirichlet distribution, then we can compute everything. We get this what's called their conjugate pairs, and we can get a really nice scheme that I'm going to go through here. So if you have a Dirichlet prior and a categorical likelihood, you get Dirichlet posterior, and then you can throw another coin toss, if you will, or a die toss, which is a categorical likelihood, and you multiply and you get a new posterior, which will be Dirichlet. And so you can keep going that way, and you can do that both for the 2K case, let's say for the coin, as for a multi-dimensional coin. What's also interesting, if you then do prediction with that result, you get this. This is the Laplace's rule of succession. And if you would have no prior, yeah, you would get basically do maximum likelihood estimation. You would get MK, so the prediction for that the kth phase turns up after having seen a data set would be MK divided by M. So and the number of times that you see, let's say, heads divided by the total number of coin tosses. However, with a prior, it would be MK plus alpha K. Alpha K is your assumed number of heads before you actually start throwing heads. And as you can see, and so the sum over alpha K is then, the total number of assumed pseudo observations. So as you see, the formula is sort of symmetrical with respect to M and alpha. There isn't a preference for pseudo observations over observations. They count in the same ways. And you can, and after, I mean, if your number of real observations really become much larger than your number of pseudo observations, then the maximum likelihood distribution, you're going to get closer to the maximum likelihood distribution, MK over N, right? So you also see that there's a difference here in whether you assume, let's say, two observations, one heads, one tails, where MK would be 1 and the sum over, alpha K would be 1 and the sum over alpha K would be 2, or whether you assume alpha K, alpha 1 is 1,000 heads and 1,000 tails. Then it takes much, in both cases, you kind of have a uniform distribution start. But in the second case, so if you've already assumed 2,000 observations, it's going to be you need a much more real observations to, let's say, to switch away from this prior to, let's say, to the likelihood, right? It would take a lot more data to turn away from your prior belief that this is a fair coin. So, and this way you can actually play with the prior to not only set your distribution of whether this is a fair coin or not, but also kind of set how sticky that is, right? How much information do you need in order to overturn that belief? So that's all sort of inside this Laplace rule of succession. Yeah, with that, I'm going to just turn it over to you. and let you ask questions. And as before, let's do it either in the chat or just turn on your microphone and say what you want to ask about this class. Or you can also just have a comment. That's also fine. Okay, I don't see something in the chat yet. So let me turn that around. Was this a class that people could follow, that you could follow? Just say yes in the chat. Okay, super, super. I think that's fun. That's actually, if you can follow this class, then we're totally on schedule, because conceptually it contains almost everything. It contains base rules, it contains machine learning, it contains setting priors, it contains this very kind of unusual trick of a one-hot encoding scheme, which is very important when you deal with discrete data. So it contains everything almost. So that's really good. Then I think let's go to, if there are no other questions,